Hi viewers, this is Sri Ramlu, degree lecturer in physics. My YouTube channel is s.s space physics. Okay, friends, watching this before watching this video, please subscribe my channel and encourage me for doing more videos. So now, change in entropy in reversible and irreversible process. Okay, here both processes are explained. So how the entropy changes in reversible process, how the entropy changes in irreversible process. So let me explain them one by one. So first in reversible process. So reversible process, let me explain first. Let us consider the change in entropy of substance when it is taken through a reversible Carnot cycle ABCD as shown in figure. So this figure is shows, right? Starting from the initial state A. So from this, the working substance undergoes an isothermal expansion AB, absorbing an amount of heat Q1 from the source at a temperature T1. So already we know the Carnot engine. How does it works? Carnot engine. So only on the basis of the Carnot engine only it is explained. Okay, friends. In Carnot engine, there are the four processes we have. One is isothermal, adiabatic. One is isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compressions. Like this, we have the four different processes. Okay, among them, two are expansion and two are compressions. In it is A to B means it is expansion, isothermal expansion. Expansion means when volume increases, that is expansion. Okay, in this process, what happens? Working substance can absorb the heat energy. How much amount of heat energy it absorbs? Q1 amount of heat energy, and heat energy is taken from the source, which is maintaining the temperature T1. Hence, increase in entropy Q1 by T1. Why? Because heat energy is more. The during the adiabatic expansion BC. So where to where, from here to here BC. No heat is taken or given by the working substance. Hence no change in entropy. Here entropy is increasing, but here entropy is no change. That why? Because adiabatic process takes place at constant heat energy only. But this takes place at constant temperature. It takes place at constant heat energy. So if a temperature constant, as we take the more and more heat, then its entropy increases. Here no heat change in heat, so that is why no change in entropy. Why? Because heat is constant. Okay, here entropy increases, here entropy same, no change. During the isothermal compression. Okay, so I told you just now. So first two are the expansion, it is expansion, and this is also expansion. Okay, now let me start compression. So already this over it is isothermal expansion, adiabatic expansion. Now it is isothermal compression. It is a quite opposite to the isothermal expansion. So during the isothermal compression C to D, so that means from here to here, what is happening? We are moving in backward direction. That means its volume is decreasing in this direction. Actually it is a PV diagram. It is a volume graph, it is volume axis, it is a pressure axis. So we move this side, volume decreases. If we move this side, volume increases. So we are moving this side means volume is decreasing. So volume is decreasing and it takes place at constant temperature. So temperature constant, it is a constant, but less amount of heat will take here. So that is why its entropy what happens decreases. Okay friends, in isothermal compression, heat energy is low comparing to isothermal expansion. In isothermal compression, heat is low. That is why entropy is also less. So that means it decreases. Finally, so that means this one. Now last one. Finally, during during the adiabatic compression, D to A is here to here. So once again, let me clear this one. Yes, now it is very much clear. So finally, during the adiabatic compression, D to A. So here to here, like this, D to A upside. So here we are move, if you we want to move here this side upside. So pressure increases. Working substance. Working substance, it is not a submu, it is working substance. Okay friends, please correct it. Working substance remains constant. Okay, in which adiabatic, in adiabatic heat energy is constant. I told you here. Okay, so in adiabatic heat energy is constant whether it is expansion or compression. Okay, in adiabatic heat energy is constant, then entropy is also constant. Okay, so that is why finally here see remains constant. So that means entropy is constant in which adiabatic expansion and adiabatic compression. Here heat energy, heat here entropy increases, entropy decreases. So net change in entropy of working substance in the cycle ABCD from here to here, A to B to C to D to A, is given by change in entropy is equals to Q1 by T1 minus Q2 by T2. Why? Because it is comes from the isothermal expansion. It comes from the isothermal compression, right? So it is a more, it is a less. So if you take difference, that gives change in entropy. But we know that Q1 by T1 is equals to Q2 by T2. So already this is explaining thermodynamic scale of temperature. Okay, so that is why Q1 by T1 is equals to Q2 by T2 means it becomes, above equation becomes 0. Okay, so when these two are equal, okay, when these two are equal, then what happens? This what becomes equal to 0. Okay friends, so that is why in reversible process entropy is constant or 0. So it's a delta S 0 means S is constant. Hence the total change in entropy of working substance in the Carnot reversible cycle is 0. So change is 0, but it is always constant. Alright. So similarly, change in entropy of combined system of source and sinks is always 0. So here only I have taken one source and one sink I have taken, and I calculated its change in entropy as 0. Okay, change in entropy is 0, but entropy is constant. Change in means its differentiation is 0. So when differentiation is 0 means its value is constant. But here combined means if you take large number of systems and if you add their entropies, then what happens? Then also it becomes 0. And now in irreversible process, okay, what about in irreversible process? In all irreversible processes, the entropy of system increases. Okay, so in irreversible process entropy of system increases here, but in reversible process it becomes 0, change in entropy. Example of irreversible process are, see here examples given: conduction of heat, radiation heat, radiation of heat, diffusion of gas, production of heat by friction, flow of electricity in conductor. So these all are comes under irreversible process, means a process which cannot be reversed. Okay, which cannot takes back direction, that is called irreversible process. Okay, a process which cannot be exactly in reverse, that is irreversible. Okay, so in irreversible process examples are conduction of heat, radiation of heat, diffusion of gases, production of heat by friction, and a flow of electricity in conductor. A process is said to be irreversible when it cannot be retraced back exactly in opposite direction. In this process, heat energy is always used to overcome friction. So just now what I explained the definition, that is the definition. Here also definition is given. Once again, the process is said to be irreversible. So it is when it cannot be retraced back exactly in opposite direction. Okay, which cannot be reversed process, that is irreversible. Let us suppose that in a simple irreversible cycle, okay, Q1 is the quantity of heat absorbed at temperature T1 and Q2 is the quantity of heat rejected at a temperature T2. Okay, so here Q1 is a quantity of heat absorbed at T1 temperature. Q2 is rejected to the sink at a temperature T2. So it is the source temperature, sink temperature. Source heat, sink heat. Okay, the efficiency of cycle is. So for this efficiency is this one. Okay, so when a substance working in between the two different temperature having the heat energy Q1 and Q2, then efficiency can be written as eta is equals to 1 minus Q2 by Q1. But we know that efficiency of reversible Carnot cycle is given by. So it is not reversible I am taking here. Just I have taken one is higher temperature substance and other one is a lower temperature substance, and they have the heat energies like this. Then I have written like this only. But here if I take a reversible Carnot engine efficiency like this. Okay, so it is taken in terms of heat, and let me take it is in terms of temperature. Okay friends, here we have to take in terms of heat, and here we have to take in terms of temperatures. Okay, it is some other process, and this is what irreversible process. For example, for an irreversible cycle, efficiency is less than that of the reversible cycle operating between the same two temperature limits. Hence, okay friends, what here it is just a simple I have taken means it is comes under practical means practical purpose, that is the irreversible process. So it is efficiency of irreversible, it is efficiency of reversible. Okay, what he's saying, for example, for an irreversible cycle, efficiency is less than that of the reversible. Suppose its efficiency is more than this one, he is saying operating between the temperature. So it is also operating, these two are also operating the same temperature, that is a T1 T2, here also T1 T2. From equation 1 and 2, which is it is 1 and this is second equation. Okay, second equation, right? First equation is this one, second equation is this one. So it is, you should not take like this, only we have to take this one only. So here this is and this is, then what I said here, it is irreversible, it is reversible. So that means its efficiency is more, its efficiency is less. Okay, now see here, its efficiency is what it is, its efficiency is it is what reversible,